2, 2, 1, and 1 ohms. How much voltage you want to make this thing?
4260.
4260. That means this is a single phase representation of a three-phase machine. What's my voltage going to be?
4462.
Okay, and what's the value of this going to be?
2 times something.
2 times, well, yeah.
1
What?
minus slip over slip or something like that. Yeah, 1 minus slip over slip.
1 minus S over S, is that right?
Yeah.
Okay, so what speed do you want to make this thing?
Alright, go. 3600 RPM.
So synchronous speed 3600 RPM, what speed do you want it to run at?
3400.
Okay, so it's running at 3400. And it's a 3600 synchronous speed. It's a two-pole machine. What's the equation for frequency or for synchronous speed?
20 times 60 hertz over number of poles.
120 times F over P would give me my synchronous speed, which would be 3600 RPM. Okay. So, what do we need to do to start?
Find out that thing on the right.
I got to find out the value that in the resistance on the right. And I didn't put in any. Let's say I've got stray loss. Well, I don't know. That's just a guess. I could guess really wrong here. Say I've got stray loss of let's just say 200 watts, and hope we're lucky that we work this right. If what's stray loss again? Windage, friction. What's it the difference? If I look at the model, where does stray loss occur here?
Nowhere in there.
It occurs after this point here. So the stray loss is between here and the shaft. Okay, so what do I need to do first?
Find the slip.
And what's the equation for slip?
It's like synchronous speed minus run speed over synchronous speed.
Are you asking me?
Yeah.
Good to tell me, because I don't remember. Look it up in your notes and tell me what it is.
Yeah, over synchronous.
Okay. So what's my slip?
5.5% or 0.055 or 0.56.
0.056?
Yeah.
Okay, or 5.6%. Okay, good. So then what does that, if I plug that into that equation, what does it make the value of that resistor?
33.7.
33.7? Is that right? One minus 0.056 divided by 0.056
33.7
times 2. 33.7. Okay. Okay, so now where do I go? That's should be getting.
Simplify all into one and find the current coming in, and then find the current number 2.
Okay, so if I take, is this real or reactive? Is it,
Yeah.
what angle is this going to be at?
Real?
It's all real because it's
Yeah.
a representation of the power output, the real power output of the machine. The only thing between here and here are real watt losses. Between here and the shaft are real watt losses. So this has got to be real power. So if I take 33.7, add 2 and plus J1, put that in parallel with this, and add that to it, what do I get for the equivalent value of this thing? Equivalent impedance.
.7 angle 4.65.
Anybody else get that? Okay, then what do I do from here? Okay, what angle am I gonna use to put on my 2462?
0.
0. So what's my current?
Angle negative 4.65.
Okay, so that means this current here, 65.2 at an angle of negative 4.65. So I can find my, found my input current. What's my power factor?
Cosine negative 4.65.
Cosine 4.65, which is
0.99.
okay. So, and it's going to be leading or lagging? Lagging. So this is already kind of an unrealistic problem because my power factor is so high. But in any case, well, it doesn't matter. We can continue to work. So now what do I do?
Find the current going LA.
I just did.
The next one.
Okay, I got to do something before I do. Well, how do I find that?
Current divider.
Well, yeah, I could do that. Yeah, right.
Whatever.
I could use a current divider. So let's go ahead and do that. If you want, if you want to go that route.
Which current are we looking for?
That one is the one he says he's going to find. Doesn't matter. We got to find them both.
Cool.
He's gonna use-
Specify it?
What's that?
Am I supposed to find it?
It's your suggestion.
So?
You're probably the only one here who remembers the current divider rule.
Not
I'm trying to think of it. I get
Okay, what is the current divider rule? It's going to be this times
that over.
this divided by the sum of both of those, right? Of all of them.
Yeah.
And make sure you got the J's in the right place. You better put your cheat sheet on, write this on your cheat sheet if you can't remember the current divider rule for the exam. This is way you're right.
I just used the voltage drop one.
That's the way I would have done it, but
Yeah,
that,
so-
this will work just as well.
So 65 at an angle of -3. Anybody else?
Okay, so if I want to get that current, how do I do that?
Get subtract the two.
Just subtract that from this, and what do I get for the current through my
Or
excitation circuit?
Calculator, so about one. 2 angle of -91. I don't know how everybody gets answers so fast. I like to double check stuff.
Yeah, but I like the first one.
Sometimes I wonder about the accuracy when
Throw it out
somebody just looks at it.
Yeah, I'm like, really, did you even read that first, or?
Okay, so I've got all my currents now. Where's the air gap?
And,
Where's the air gap line?
so between the J1200 and everything on the right,
Okay, so the air gap is right here, usually where we draw it. So if I wanted to find the power across the air gap, how could I find that?
that current.
R squared R?
Okay, give me the I's and the R's.
65 squared times J1 plus 2 plus 33.7.
Well, 65 squared times J1, what will that give me? Won't give me real power. Well, what will it give me? We just got through working a problem using I squared x. What did we get?
Les Vars.
We got VARs. So will that give me the power across the air, the real power across the air gap?
Why not?
It won't.
R is just the 35.
So what will? 65 squared times what?
35.7?
35? No, 35, yeah, just you summed them up, that's fine, 35.7. Or 33.7 plus 2. So what's my power across the air gap? And I'm gonna have to multiply it by 3, three-phase machine.
Watts.
450 kW. If I want the power into the shaft, or into the rotor, what would that power be? What's the equation gonna be? It'd be the 65 squared times what? Which part of this thing models the rotor? The power out of the rotor.
The variable resistor.
The variable resistor. That's what this is. This is the model of the power that's being developed in the rotor.
Okay, so it's just the 33.7.
Right. This is just losses in the copper.
Okay.
This is the modeling the power that's going to do some kind of work, either take care of friction or actually turn my load. So I'm going to take this and multiply by 33.7 because that's the value output of my rotor. So what do I get for power being developed in the rotor?
Uh, 427.
427 kW. Now if I want the shaft horsepower, or the power developed to the load, how do I get that?
Subtract the losses,
Which losses?
the ones at the top of the board. Forget what they're
Stray
called.
losses?
Yeah.
I made them too small. I'm gonna change that. The stray losses for this machine will be 2,000 watts
Okay.
instead. So if I want the power that's getting into my load, I'm gonna take 427,000 and subtract my stray losses, which are 2,000. So what do I get for the output brake output power for this motor? 425, and how many horsepower is that?
569.
569 horsepower. So that's that's what this machine is putting out to the load with this slip.
So it's like a perfect motor that makes a whole lot of horsepower for us? With our power factor is like 99.
Well, just tell me what you mean by perfect motor. I mean, this is unrealistically high, but,
I don't know, not much loss.
but there's nothing, this is a real model, so this isn't a perfect motor. If this was, if we could build a motor that well, we could get this condition. My problem is I probably made this too high. A real motor would have more magnetization current than this one has. Okay, so when this thing is running, it's gonna be, the power it run is 569 horsepower. Developed power in horsepower would be 427, so it's about the same. Power across the air gap is 452 divided by 746. 452,000 divided by 746. Okay, what don't we know about this machine? We don't know the starting current. If I want to find the starting current of this machine, how do I find it?
Redo everything without the variable resistor.
Okay, what's my slip at start?
0. Or, what is it? Okay.
If it was 0, this would become infinite, right?
I think it's 1.
Slip is 1. So that means this becomes 0. So that's my circuit at start. So what's my starting current going to be? Do the same thing. What's the value of this equivalent value of this going to be?
.4 angle 26.
Okay, so what's my current starting current?
550.
550?
Yeah.
At what angle? Negative 26?
Yep.
Okay, so my starting current is 550 amps. So how many times running current is that? 550 divided by 65.
8.8.
8.8. So is that high or low for starting current? High. What would you expect it to be?
5 to 6.
Around 6. So again, a little bit unrealistic. Actually, that's really not that unrealistic. There are some motors that have that high starting value. My starting power factor is what? Cosine negative 26, which is
29.
leading or lagging?
Lag.
0.89.
Yeah.
Yeah. Negative 26.6.
Yeah, I guess that's right. That's 2, that's high. 0.89 lag. And what would I expect that number to be?
The power factor?
Yeah, starting power
A
factor.
lot lower.
Yeah. How much lower? What would I expect it to be?
Half, at least. I don't know.
0.2.
Where is it?
or 0.
Oh, yeah.
Usually we assume 0 for starting power factor for a motor, but 0.2 is typical. So again, that's not really very realistic. But for our motor, that's what we came up with.
But the math's right.
What's that?
No, I said the math is right, so.
Yeah, our model is just not a real model. Okay, I think we got everything. Is there anything we missed? Oh, losses. What are the losses inside the motor? I wanted to find the efficiency of this motor.
Do I squared R's for the resistances?
Okay, so I know the output power. I know the power across the air gap. So the only thing I have to add to that to get the power input is what?
Whatever.
This power loss right here, right? 65.2 squared times 2 times 3 would give me the loss in the whole motor for that. What is this the model of, by the way? What is this the modeling?
Stator?
The stator impedance, the stator reactance. This is
The actual coil?
stator resistance. The losses in the stator resistive losses in the stator. Okay, this is what? What is this a model of? This piece.
The amount of current it takes to set up the magnetic field in the thing, or?
Okay, it's going to give me the equivalent reactive losses due to magnetization. What's this?
Rotor?
That's going to be modeling the reactive losses in the rotor. What's this?
Rotor impedance or resistance?
The copper losses in the motor, in the rotor. So all these things are losses of some kind. They're using either watts or volts. And I'm picturing the stator var loss, the stator real power loss, the magnetization var loss, the rotor var loss, and the rotor copper loss is what one way of thinking of what those things are. Okay, where were we at here? What we're trying to figure out?
Power factor?
Oh,
Or
trying to find
efficiency?
efficiency.
Yeah.
So I know my power, my real power going across here is 452 kW. So what's my loss in the stator, my real power loss in the stator going to be?
$25,506.
25.5 kW.
Yeah.
So my power input is going to be the power across the air gap plus that. Which is what?
477.
So what's my efficiency? It's going to be my brake horsepower divided by my input power. So my brake horsepower was brake 425 kW divided by 477.5. What does that give me for efficiency?
0.89.
89%?
Yeah.
That's pretty typical. So that's not even. Anything else that we missed here? Any other number that I can't think of anything. What's that?
This one we did. We got to keep us the slip.
Okay. Any other questions on the induction motor? And when you're using it, just keep in mind what it is that each of these pieces is a model of. Okay. Any other questions? And this is going to be 600 amps At unity power factor, that means this angle is also gonna be 0. And I'm trying to find out what this is, voltage magnitude, and then what the voltage regulation would be. So let's start with how would you find the value of that?
Which value?
What's that?
Which value?
Well, I have to find these two things.
Right, V-reg.
So I'm trying to find the delta is the rotor angle,
Delta's the rotor angle.
you know,
That's good.
and voltage what's the equation for voltage regulation?
No load minus full load over full load.
V full load minus V no, or the V no load minus V full load.
That was no load.
V no load minus V full load over V full load, right? Okay. So that's the voltage regulation, I think, that we're trying to find. So how can I find the angle of this voltage? How can I find the whole thing, that voltage?
Current times that, times
The current times, what is that?
the. Reactive.
Okay, so
45 plus J8.
are you telling me 600 at an angle of 0
Yes.
times 5 plus J, 0.5 plus J8?
Yes.
And that would give me the voltage drop, and then what do I do with that?
Subtract it from 30 and 6360.
Add it. Or add it.
Subtract it or add it? How do I know which way, how much do I know which way to do it?
Depending on where you're going, so you need to add it because it'll be lost when you're coming from
Exactly,
there, it'll
because-
end up with 6360.
The way I've got my arrow drawn, I'm gonna have a voltage drop in that direction.
Yeah, so you add that
I've got it.
6360.
Exactly, so I'm gonna add that at 6360 at an angle of 0. And what will I get?
$8209.
At what angle?
35.8.
5.8. Now, if I wanted to get the voltage regulation, so I found delta. Delta is 35.8. I want to get voltage regulation, assuming this is full load. I don't know if did the problem say this is full load? Probably. Or if it didn't, should have.
It did not specify.
Okay, well, assuming this is full load, I'm going to have to figure out what the voltage at no load is. So how do I do that? If I got 6360 at full load, what's my voltage going to be at no load?
Would it be the same because it's an infinite bus?
Well, it doesn't matter if it's an infinite bus. I'm gonna disconnect my generator and have no load.
Gotcha.
So if I were to do that, if I were to take this, whatever's on here, off of here, I mean, this becomes 0. And what does this voltage become?
8209.
8209. Because I got no voltage drop if I got no current flow. So unless I change my field current, this is going to stay 8209 and this is going to become 8209. So that's my no load voltage. So I'm going to take 8209 minus 6360 divided by 6360. That should give me my voltage regulation.
About 29%.
What's that?
29%.
29%? Is that what the answers they gave?
Close. 25% what you get.
25%?
Yeah, they're all just a little off.
Okay.
We're above on both of them.
What angle did I have?
You had 31.7.
31.7? Well, I'm saying this is probably right. My answers are probably a little off.
And for some reason, I think your answer for B was in fade or something. What was the answer for B, you guys? Yeah. And what was it asking for? The generator
My answer for B,
Internally
what's,
generated voltage.
what's B?
We don't have the internally generated voltage yet.
Okay, let's take it to a
Well, this is
max.
the internally generated voltage line to neutral. If I went line to line and multiply this by the square root of 3, what would I get?
Okay. 14.2. Okay.
For 2K.
I was just making sure that was.
This one's probably the 8209.
What number was that?
First one.
Numero uno.
Start doing
No, I mean,
Fusion.
Okay, any other questions on this? Or? Got one more thing I want to see if you can work, that you better be able to work for the exam. I got a generator and I got a motor. This is let's just say this is a 480 volt bus, and my generator is generating 1,000 watts at 0.8 lagging power factor. How much current is it putting out? How do I get that? This is a three-phase machine.
Root 3 BR cosine.
Okay, what's the equation?
P equals square root 3 voltage, and cosine, and
we're three-phase?
So it's a three-phase generator. If you don't, or that's another thing, if you're not told if it's single or three-phase, it's always three-phase. If it's single-phase, I'll tell you especially. Okay, so 1,000 watts. What's my voltage?
480.
What's my current? What I'm solving for? What's my power, or cosine theta?
0.8.
0.8. What's my current?
1.5.
1.5 amps. Good. This is the equation. I've tried to design the test so you can't get any problem right unless you know that equation.
Thanks for the heads up.
Because that is the equation you'll use most. If you really become working power, you'll use that equation all the time, and you better know it.